In this video, we're going to learn about a graphical tool that helps us relate reflection coefficients, generalized reflection coefficients, load impedances, and driving point impedances. And we need this tool because we have a problem. We can calculate the generalized reflection coefficient pretty easily, and we can turn the crank on our driving point impedance formula if we have to. But these tools aren't great for design. We'd really like to have a fast way to switch back and forth between gamma and perceived impedance, either a ZL or a ZDP depending on the load. In a perfect world, this technique would be quick enough that we can apply it to measured data in our head. That points to using graphical techniques because those don't require us to do too many calculations. It turns out this technique exists and it's one of the most intimidating graphs in engineering. You might say, Prof. Spencer, I'm not intimidated by graphs. I've seen it all at this point. Heck, you've already showed me Bodhi plots. Well, feast your eyes on the Smith chart! This does look bad, but it's actually pretty reasonable. This is a plot of the complex gamma plane with resistance and reactance coordinates laid on top of it. We'll figure that out in the next few slides. We're going to take a step back to build up to the full Smith chart. We know we're making a graphical tool to relate gamma and z, so the first thing we need to decide is whether we're plotting gamma or z. I've plotted both on this page as functions of s to help us make our decision. The main thing to point out is that gamma g of s describes a circle in the complex plane. It's just a vector rotating around in the gamma plane, so it becomes a nice phasor. The plot of z of s isn't too badly behaved either. It turns into a circle somewhere else in the complex plane as s moves around. However, there's a bigger problem with plotting z, which is that sometimes we use open circuits, so we'd have to figure out how to plot infinite values if we wanted to use a graph of z. Both of these facts suggest that we should build our tool by making a graph of the complex gamma plane, and indeed that's what the Smith chart is. In order to switch between gamma and z, we're going to take the grid lines on the z plot and superimpose them on the gamma plane. So we need to figure out what this line looks like when we put it on the left graph. We're going to map those lines from z to gamma using a slight modification of our standard equation for gamma. By factoring z0 out of the top and the bottom, we get the equation in a normalized form where zn, which is equal to zl over z0, is called the normalized impedance. This form is an example of a mathematical function called a Mobius transformation. Mobius transformations have a special property, which is that they preserve circles. So anything that would describe a circle in z space will become a circle in gamma space. This is true for a very inclusive definition of circles. Most notably it includes lines, which can be interpreted as circles that pass through infinity. We're going to stretch this equation to the breaking point on this slide, but all of the manipulations are just high school algebra on the real and imaginary parts of it. So we get started by substituting Rn plus Jxn for Zn, where Rn is a normalized load resistance and Xn is normalized load reactance. We also split gamma into its real and imaginary parts. Once we've done that, we've actually stealthily converted this equation into two equations. We know that the real parts of the left and right side have to be equal, and so do the imaginary parts. We could rearrange this equation to split up the real and imaginary parts to prove that, but I'm not going to do the math here. Instead, we're just going to cut to the result. The derivation that gets you to these equations is pretty cool, but I don't have time for it in this video. So I recommend that you look through the derivation I've linked on the course site. As enticement, it includes the only use of completing the square that I've seen out in the wild. A quick glance at this result is promising. In the z-plane we had vertical grid lines with a constant resistance and variable reactance. And our first equation describes a locus of points for a constant resistance and variable reactance. The z-plane also had horizontal grid lines with constant reactance and variable resistance, and our second equation describes a locus in the complex plane with a constant reactance and a variable resistance. Both of the loci specified by these equations are circles. The constant resistance circles have a center at Rn over 1 plus Rn and a radius of 1 over 1 plus Rn. And if you add the center and radius together, you get 1 plus Rn over 1 plus Rn. So you see the point 1, 0 is going to be included on every circle, regardless of what Rn is. I've drawn a picture of that below. The constant reactance circles have some similar behavior. They have a center with a real value of 1 and a complex value of 1 over xn, and the radius is 1 over xn. Subtracting the radius from the center shows that 1, 0 will be part of this family of circles too, regardless of whether xn is positive or negative. And I've drawn that as well. These sets of circles make up our resistance and reactance grid on the gamma plane. If we overlay them, we'll get a Smith chart. We can see that here. This circle is an example of constant resistance, and this circle is an example of constant reactance. There's also shadowy lines on the Smith chart that look like a reversed version of the Smith chart. Those come from the same derivation if we opted to write gamma in terms of admittance instead of impedance. The equation at the root of that parallel derivation looks like this, and it gives rise to circles of constant conductance that look like this, and circles of constant susceptance that look like this. So in summary, the Smith chart is a tool to convert between gamma and z or y. It's a plot of normalized z or y coordinates on the gamma plane. The axes are made of circles of constant Rn and constant Xn, and you can flip it around to make a shadow Smith chart for constant Gn and Bn.